So, as of now, the natural number system is quite boring, so to say. We just have a few axioms, and we have introduced and investigated what are the most fundamental things that we have to take into account when we want to define what is the natural number system. Remember that the two basic features or reference points that you have to consider all the time is that we first must introduce a number which is 0 and the increment, so that n plus plus is the increment of n. We have now only this operation and the axioms that I was referring to. However, we can do little, not to say nothing, with this operation. It's a very frustrating one, in particular if we want to get to very high numbers. So we want to now introduce something which I'm going to call addition. And of course, all of you have had this word, and you know how to add up numbers. You know how to add 3 plus 5, 8 plus 13, etc. But again, I ask you to try to detach yourself from everything that you think you know. And I want to have a look at it from scratch. That's the most important thing. So I want to introduce now this operation, which is a complex one. And the way I want to define it, or the way it's going to work, is that to add say 1, 2, 2 should be the same as incrementing 2 one time. So I'll mention that that increment is not symmetric, but the result is the same. So let's go for it. So imagine that you have a natural number, m. So m lies in the set of natural numbers n. So m is a natural number. I'm going to define that 0 plus m is equal to m. And again, look at this symbol here. This is a definition. It's something that we're just introducing here. And by the way, and this is an exercise that I propose to the students, I am using these words, addition, add, plus, etc. Imagine for a second that I had started this lecture by saying that I'm going to introduce a complex operation which seems difficult to start with, but as we move on, things look more and more crystal clear. So imagine that we have the operation that I'm going to call I don't know, Moritin, which is a word which does not exist, I hope, Moritin. And Moritin consists in doing the following. So to moret a natural number to another number, we introduce the operator moret, so that n moret m is going to give us a result which is going to be another natural number, and although this operation is not going to be symmetric, so this is not going to be symmetric as compared to this one, the result, the moretin, is going to be the same quantity. Now, you must be extremely confused. So, you should be as confused as when I start talking about addition and this plus symbol, because it's exactly the same thing. So this is a mental exercise that I ask you to try to do. Try to detach yourself from everything that you think you know. You don't know it. I mean, you can use it and you use it, you employ it, but probably you don't understand it. So forget about that modern thing, because of course it does not exist. So let m be a natural number. To add 0 to m, I'm going to define again that 0 plus m is m. Now, as you can imagine, I am using here deduction, so that we depart from this one. I'm going to suppose that we have defined how to add n to m. So I'm going to assume that we know how to do this. And then we can add n plus plus to m by defining that the addition of n plus 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 m is n plus m plus plus. Okay, so these are the two things that I have defined right now. What does it mean? This means that 0 plus m is m, of course, and that also means that 1 plus m is going to be 0 plus 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 m, and that in turn is going to be m plus plus, and so on and so forth, right? For instance, 2 plus m is going to be 1 plus 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 m, which is m plus 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 plus. So note that this definition is asymmetric. For instance, if you are adding up 4 to 7, this is incrementing 7 4 times, while 7 plus 4, what we're doing here is to increment 4 7 times, which is a different thing. But of course, they both give you the same result. Okay. Now, the interesting thing is that although we only have 2 facts about addition, this one and this one, this turns out to be I was about to say more than, but it's not more than, but anyway, it turns out to be enough to deduce everything you know about addition. In particular, please notice that, as I said before, 7 plus 4 is the same as 4 plus 7, but there is nothing which makes this property particular to numbers 7 and 4. So that this in general is true for any 2 natural numbers n and m, so that you can interchange them in the operation. I will be proving that shortly. And okay, so now we are going to start with some lemmas. First lemma for any natural number n plus 0 is n. Now, you cannot deduce this immediately from what I explained to you before. Actually, from our definition that 0 plus m is defined to be m. Why not? Because I have not yet proved that A and B in the operation of addition are interchangeable. We don't know that. So you cannot deduce this from our first definition. So I leave this up to you. I want you to prove this alone. And as a hint, well, you should use induction. Next lemma. For any two natural numbers, n plus, n, no, I was right, n plus m plus plus is equal to n plus m plus plus. Again, you cannot deduce this from what I introduced before, namely n plus 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 m was defined to be n plus m incremented twice, 2 times, right? So as before, I let this up to you to prove that this is right. Try to use induction by keeping one of them fixed. For instance, actually not instance, m. And that should be enough for you to prove this lemma. Also in particular, note that the sum of two natural numbers, a and b, is going to be a natural number itself. It's going to lie in the set of natural numbers, and you can prove that as well by yourself. So please prove it. And as a corollary, of the previous two lemmas, we can see that n plus plus is exactly the same as n plus 1. And again, I ask you to prove this. Okay, so let's go for a proposition. Addition is commutative. For any two natural numbers, n and m, we have that n plus m is the same as m plus n. And again, you can prove it by using induction n and keeping m fixed. As usual, you prove first the base case, so n equals 0, so that you have to show that 0 plus m is equal to m plus 0. By the definition of addition, 0 plus m is m, while by the previous lemma, m plus 0 is m, so that we have the base case. Now we're going to suppose inductively that n plus m is the same as m plus n, so that all you have to do now is to prove that n plus m is the same thing as m plus n incremented twice, to close the induction. So all you have to do now is to take into account the definition of addition. N plus plus m is, as defined, n plus m plus plus. And that by one of the two previous lemmas, m plus n plus plus is equal to m plus n plus plus. But this is equal to n plus m plus plus by the hypothesis that n plus m is equal to m plus n, the inductive hypothesis, this one here. So n plus 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 m is equal to m plus n plus plus, and we have our proof. So another proposition: addition is associative for any three natural numbers, say m, n, this is supposed to be an n, and an l. We have that m plus n plus l is the same as m plus n plus l. And you can prove this yourself. Yet another proposition, the cancellation law. If m plus n is equal to, so if we have three natural numbers, we have that m plus n is the same to m plus l, then we have, what do we have? We have that n is the same as l, and that you can prove this yourself. Now, please take into account that you cannot use subtraction or negative numbers to prove this, so that you will have to prove this again by induction on A, on M. Get confused sometimes. So you have to prove it by induction on this number. So you consider the base case, then you suppose inductively that you have the cancellation law for A, again for M, and then you go to the next level. That is what you have to do to prove the induction. So now we want to see what is a positive number. And again, you know this word, you have to use it an infinite number of times, but I am asking you to detach yourself from all the things that you know already. So a natural number, A, n, or whatever, is said to be positive, is positive if and only if, which I use in this short form if with double F, is not equal to 0. Okay, so this is a definition. And this definition is very powerful because it allows us to do a lot of things. In particular, it allows us to have a few new things coming in. For instance, if A is positive and B is a natural number, then A plus B is positive, and therefore B plus A as well. So how you do that? Again, by induction on B. Let's consider the base case. Suppose that B is equal to 0. So A plus b is the same as a plus 0, which is a, which we have defined to be positive. So we have proven this case. Now we want to suppose inductively that a plus b is positive. And then we move to the next level. A plus b plus plus is the same as a plus b incremented twice. And this cannot be 0, but the previous axiom. Remember, 0 cannot be the increment of any natural number, the successor of any natural number, which means that the n plus plus cannot be 0 for any natural number n, and this here is a natural number, because the addition of two natural numbers is a natural number itself. This is a very nice example for you to realize that we're doing things in a consistent way. So our theory is robust, and we are developing, we are working out a number system which is consistent, which we can trust. A corollary of this is the following. If a and b are natural numbers, such that a plus b equals to 0, then a is 0 and b is 0. And you can prove this yourself by contradiction, by supposing that a is different than 0 or b is different than 0. A lemma that we can introduce now is that if you have a positive number a, so a is a natural positive number, then there is exactly one natural number b such that b incremented twice is a. And this you can prove yourself. Alright, so now we have introduced addition, and we have a clear picture of what addition is, this complex operation, because it's a complex one. Again, it is trivial to you because you are extremely used to add things. But if I had changed the name and changed the symbol, you probably, I have even had students who did not realize that I was talking about addition, because I just changed the name of it and the symbol. So it is just a problem of you being used to doing these kind of things in a mechanical way. And this is what I want to avoid. It is, of course, useful that you can do that, but you must try to take a step back from all of that to understand the way we are proceeding here. And why is that? It's not because I want you to be bored or because this is fun by itself. It's because the way that I am introducing, well, actually Tao is introducing the natural numbers, is going to be extremely useful when we move on forward and we take a look and develop the axiomatic set theory. You will see that the way of thinking and working out things is going to be very, very similar to Peano's axioms and the constructing of the natural number system. Okay. So after all of this, we can now begin defining a notion of order. And order is going to be a very important concept. All of them are important, but I'm just trying to draw your attention. There is somehow a correspondence or a kind of equivalence between what I'm going to say and the notion of I don't want to advance the results or theory now, but let's say that the ordering of the natural numbers, you want to see a very close equivalence between what I'm going to do, what I'm going to talk to you about the natural numbers being ordered, and what we will see in set theory. So let n and m be natural numbers. We want to say that n is greater than or equal to m, and write it like this, using this symbol, or in an equivalent way, like this, if and only if n is m plus a for some natural number a. Now, we say that n is strictly greater than m, and we write it like this, n is greater than m, strictly greater than n, if and only if the previous is true and n is different than m. In this case, we say that that n is strictly greater than m. And for sets, we have a very similar concept. So it's an interesting result associated to what I just said, namely this. Consider, for instance, the number 13. 13 is larger than 10 because, of course, 13 is the same as 10 plus 3. And 13 is different than 10. So 13 is strictly larger than 10. Now, note that n plus plus is going to be strictly larger than n for any natural number n. Think about this. What is this telling you? Why is this true? N plus plus is larger than n, strictly larger than n, for any n means that there is no largest natural number n, because the next number n plus plus is always larger, and that will always be true. And now we go to the basic properties of order for natural numbers. The first one is that the order is reflexive. A is larger or equal than A. Order is transitive if A is larger or equal than B and B is larger or equal to C, then obviously A is larger or equal to C. Order is antisymmetric if A is larger or equal to B and B is larger or equal to A, then we have that A equals B. Addition preserves order. A is larger or equal to B if and only if A plus C is larger or equal to B plus C. The fifth one is that A is strictly smaller than B, or B is strictly larger than A, if and only if A++ obeys this. B is larger or equal to A++. And the last one, A is strictly smaller than B, or B is strictly larger than A, if and only if B equals A plus D, say, for some positive number D. Now, I would encourage you to prove all of them, and in particular the last two ones. These are very interesting. And this proposition, so from 1 to 6, plus the following one, allow us to introduce the strong principle of induction, which is a very useful one. So let's see the last proposition, the trichotomy of order. Consider two natural numbers, A and B. Any two natural numbers, then exactly one of the following statements is true. Either B is strictly larger than A, or A and B are equal, or A is strictly larger than B, for any two natural numbers A and B. Now, I want you to try and prove this. And see what you come up with. In any case, and as I just announced, these properties of order allow you now to derive the strong principle of induction. So let M0 be a natural number, and let P of M be a property pertaining to an arbitrary natural number M. Now, suppose that for each M larger or equal to M0, we have the following implication. If P of M prime is true for all natural numbers obeying the following M0, M prime, and M, if this is true for all natural numbers obeying these, then P of M is also true. Then we can conclude that P of M is true for all natural numbers larger or equal to M0. So, the truth is that in mathematics, usually M0, usually but not always, M0 is going to be either 0 or 1. But in any case, so this is the strong principle of induction, and I let the proof to you. Now that we have finished with addition, which is an iterated increment, I'm going to introduce multiplication, which is just an iteration on addition. So we start again as we did with addition. Consider a natural number m. To multiply 0 to m, we define 0 times m to be 0. Now, suppose that you have defined how to multiply n to m, which we have not. But then we can, because again, this is, I didn't mention it, but I am implicitly using here induction. So suppose inductively that we know we have defined how to multiply n to m. Therefore, we can multiply n plus to m by defining the following. So that, for instance, 0 times m is 0. And therefore, 1 times m is going to be 0. 2 times m is going to be 0, etc. By induction, you can straightforward prove that the multiplication, the product of two natural numbers, is again a natural number. So I'm going to mention now all of the propositions and lemmas without giving you any proof for them. You should try to prove them yourself, but I'm not going to do it. So, first lemma is that multiplication is commutative. If you have two natural numbers n and m, then n times m is the same as m times n. And this side note, I'm going to skip this now. I'm going to just write n times m like this, which is something which, by the way, drives my daughter crazy, because she insists upon having that cross or point pinpointing the multiplication. But you should get used to just interpreting n times n as this, the same way that a times b plus c is going to be written like this, and I will be meaning, of course, a times b plus c, and not, which this was a hair problem yesterday, but a times b plus c. This is wrong. This is a way of writing the thing that we have here. So, another lemma, positive natural numbers have no zero divisors. Divisor. Apologies for my horrible English. So, consider two natural numbers n and m again. Then n times m equals 0 if and only if at least one of them is equal to 0. In particular, if n and m are positive, then n times m is also going to be positive. Okay, distribution. As you can notice, I am speeding up because I'm hungry. For any natural numbers a, b, and c, we have that a times b plus c is a times b plus a times c, and that b plus c times a is b times a plus c times a. Multiplication is associative for again these three natural numbers, a times b times c is a times b times c. And what I want to write this for short, a times b times c, because it's associative. Multiplication preserves order. If a and b are such that a is strictly smaller than b, and that c is positive, then a times c is strictly smaller than b times c. And therefore, we can derive a corollary, which is a cancellation law. If you have three natural numbers such that a times b is the same as b times c, and c is non-zero, then a is going to be b, and you can prove this yourself. And as you can notice here, in some way, we have introduced, in a subliminal way, probably, something like a division, which I have not defined. But this is the same thing, of course. When we went to primary school, and they told us that if you have this kind of equation, then x is equal to 1/3, because you divide on the left and on the right by 3. You are dividing right. But in particular, what you are doing is this kind of thing. You are implicitly using a number of axioms that nobody explained to you. They just came out of thin air, and this is what drove me very, very confused during many years. Of course, not with addition and multiplication. I managed to, I wouldn't say master, but at least to come along with these two things. But later on, the lack of explanation of where things came from, in my case, was a very serious problem, which made of me actually a very bad student. In particular, note that with these propositions, you can deduce all of the rules that you know of algebra involving addition and multiplication. Also note that we have derived all of this from the very primitive notion of increment. We are going to, of course, drop that one, because whenever we see n++, we're going to use n+1, because it's the same thing. We have seen that already. Another interesting proposition is the Euclidean algorithm. Consider that you have a natural number n, and q is a positive number. Then there exist natural numbers m and r such that r is less than or equal to r, and r is strictly smaller than q, and n is equal to m times q plus r. What this is telling to you is that you can divide a natural number n by a positive number q to obtain a quotient m, which is in turn again a natural number, plus a remainder r, which is less than q. Now, notice how simple this proposition is. And however, this proposition, which is an algorithm, allows you to develop number theory. The whole of, well, at least is the milestone which is marking the beginning of number theory. And to finish with, I'm going to define exponentiation for natural numbers, of course. Let m be a natural number. So to raise m to the power 0, we define m to the power of 0 to be 1. Now, have you ever wondered, in all of the exercises that you have done as a student, primary school, high school, etc., why any number to the power of 0 is 1? Well, this is the reason. It's a definition. And in particular, we define that 0 to the power of 0 is going to be 1. Now, suppose, and whenever I talk about 0, you should already start, being suspicious. Why is he mentioning 0? Well, because of the usual reason. I'm going to use induction now. So, we start with the base case. Define 0 to the power of 0 equal to 1. Now, suppose recursively that m to the power of n has been defined for some natural number n. Then we define m to the power of n plus plus to be m to the power of n plus times m. Do you remember that thing about if you have the same base, you can add up the powers? Well, this is the reason for it. Okay. So, we will not continue talking about exponentiation here, but we will have to wait until we have defined integers and rational numbers. And this is the end of the natural numbers. In the next summary, I will cover what I have explained about set theory, axiomatic set theory. Okay, so goodbye and see you next time.